So obviously you can see from the title here that this Explain Everything video is going to go over very quickly vector addition. I'm going to start with the idea of collinear vectors, and that's the idea that when you have, say, vector A, which is a component, and you add to it vector B, the result is the sum of those two. This result is also called the resultant. So whatever A plus B is just equals the addition of those two. And likewise, if you are subtracting, you might say A is like this, B looks like this. The result, in this case, will be a tiny little rightward facing vector. Now, that end piece is important because you need to define direction. So if you look up here with A and B, you see that A is headed to the right or maybe on the positive x direction. So is B. So the resultant, while it has a magnitude that is the addition of A and B, or the sum of A and B, it must also contain a direction. So if you're looking to make this appropriate, you would say the resultant is so large plus what direction it's facing. Because if you see here with the subtraction piece, if A was actually smaller than B, then the resultant would actually be facing to the left. So because these are vectors, we must identify both a magnitude and a direction. So what about the idea of two-dimensional vectors? When, say, you have driven east, let's say we've driven 10 kilometers, and this is in the easterly direction, and then you stop and then you take a left-hand turn and you drive due north. That's a terrible north, sorry. You drive north and you do that for, let's say, 4 miles, or 4 kilometers, excuse me. The addition of those vectors seems pretty straightforward. If the question was how far did you drive, then it would be the sum of 10 kilometers plus 4 kilometers. And this highlights the difference between vectors. Distance is a scalar quantity. So the distance might equal 14 kilometers, but the displacement, which is the actual vector here, is this. How far am I in a straight line from where I began? So displacement, which is separation from the origin, is going to be whatever that hypotenuse is here to our right triangle. Now obviously these situations get more complicated, but so you should be able to identify this as something that you've done before. If you're looking for the third side of a right triangle, this is good old Pythagorean theorem. So if we are looking for what we're calling our resultant, which is the addition of these two vectors, we're going to say that r, in this case, is going to be equal to square root of 10 kilometers squared plus 4 kilometers squared. So that's 116. Take the square root of that. And you are looking at 10.7 kilometers. Now we're ignoring significant figures here. However, what you can say is that through the addition of these two vectors that are at right angles to one another, your displacement is 10.7 kilometers from your starting position. It just means that if you were to walk this blue line right here, it would take 10.7 kilometers to get here. Now, remember that displacement is in fact a vector. And here is the frustrating part about this. for some of you who've made this connection immediately and you can follow this, the unfortunate piece is that because this is a vector, you must also carry with it a direction. So I kind of want to show you that. You can think about a direction in this case as more like a heading. If you're going to say, hey, I need to end up here where that little asterisk says, and you're going to walk 10.7 kilometers, you better know specific directions or else you could end up anywhere in this 360-degree circle. So the way we do this is we employ one of our trigonometry functions. It's a pretty common one for determining an angle from your starting vector. But if you look at this, this theta, which is a terribly drawn theta, if you look across from here, that opposite wall in this 3-side room is the 4 kilometers, and the adjacent side is the 10. So if you remember, tangent is equal to opposite over adjacent. So that's from the TOA. And what that really means is tangent of angle theta is equal, or in this case really proportional, to the opposite over the adjacent. So that would be tan theta is equal to 4 over 10. So once you have both the opposite and the adjacent here, and we know that those are 4 and 10, you see that the equation says tan theta equals 4 divided by 10. For those of you that understand this, you'll know that the method now used is to take the inverse tangent of 4 divided by 10, and that will actually give you theta. And in this case, theta is equal to 21.8 degrees. So the final answer here can be stated as 10.7 kilometers at 21.8 degrees, 21.8 degrees north of east. So, why don't you try this one? We have a person that walks, I apologize. Person that walks due east for 3.0 kilometers. And then they walk due south for 1.0 kilometers. So you can imagine this person's walking through a neighborhood. Well, if we wanted to get to that person in the straightest path possible, how could we run through people's backyards to get here? So a reminder that we identified this direction as east and this direction as south. So when you solve for your final answer, I am looking for the vector's magnitude. So what is the displacement, how many kilometers, and at what angle relative to the directions given. If you've gone ahead and solved this correctly, you should know that your position where you ended up right here ends up equaling 3.2 kilometers at an angle of 18.4 degrees south of east. I hope this helps you out. Thanks. We'll see you in class.